So this question, we have an internal sphere, and then there's an outside sphere, or its outside shell, kind of looking like this. So the question says there's a solid conducting sphere carrying a net charge plus Q. So this guy, this sphere here, has a charge Q and has a radius of A. So in here, this radius of A. The sphere is placed inside the conducting shell of inner radius B. So inner radius B, another radius C, outer radius C. The shell has 0 net charge. So net charge outside the shell is 0. Asks for derive an expression for electric field at various distances where R is less than A. So inside the conducting sphere, R is between A and B. So within this within this vacuum, between B and C, so within the shell, and then outside. So this uses Gauss's law. Gauss's law states that the flux states that the electric flux, let's see, written like this, is equal to the charge enclosed over the permittivity of free space, or epsilon 0. Now the electric flux is also equivalent to the surface integral of the electric field over the surface. So if I rewrite this, this is the surface integral, this is the dot product between the electric field and the unit normal vector of the surface. Exactly what this surface integral is, how that's created, is learned in multivariable calculus. But we do know that the dot product is kind of basically, if the electric field, the surface here, this is the unit normal vector n of some kind of surface. If the electric field is not perpendicular, then there's an angle theta here, and the dot product will take into account this angle. It'll take the cosine of that. But in this case, we'll see that this is not necessary. What this is saying is that you take you integrate. For example, if we have the sphere here, and we've got the surface area of the sphere, and if we take one tiny portion, the infinitely small unit surface area, and we have the electric field through that surface area, if we add up all of these infinitely small units, we'll get the total flux through this surface. So the beautiful thing about this sphere is that because this charge is in here, the electric field is in line with this unit vector, with this, what is it called? It's called the unit normal vector of the area. And so the theta is in essence 0, cosine theta is just 1. So really this is just E times everything else. So we don't have to worry about angles, is basically what I'm saying. So really the integration over this is just going to be E times, if you integrate over all this area, you just get the surface area of a sphere. And the surface area of a sphere is equal to 4 pi r squared. Alright, so we're going to use this is equal to the charge enclosed over permittivity of free space. So if we look at the question asks, it is a solid conducting sphere. Now when an object is conducting, it means all of the charges in it can move around. So because charges, you know, if this plus Q, if it's got positive charge, all the positive charge wants to move away from each other, because of, you know, it's like charges repel each other. So all the positive charge is going to go to the surface because they want to be as far away from each other as possible. If this was a non-conducting sphere and the charge was uniformly distributed, then the charge would be, you know, uniformly distributed. But because it's a charged conducting sphere, everything is on the outer rim, and so there's no charge inside. So if we look at where r is less than a, meaning we're inside the sphere, the charge enclosed within that sphere is going to be 0 because there's no charge in here. So the electric field, 4 pi r squared, will be equal to charge enclosed, which is 0, over this, it'll be just 0. So E will just be 0 because this radius has value. So E has to be 0. So when R is less than A, E is equal to 0. Now let's look at when R is in this vacuum between A and B. So in that case, we're going to have a sphere here, and all of the charge is going to be enclosed. So again, we have this. Charge enclosed is equal to Q. This. So if we move everything to the other side, Q over 4 pi r squared. This kind of looks like KQ over r squared. So really, it's just, so when A is less than R, less than B, we have that the electric field is really, you know, just the electric field due to a point charge. Or it looks very similarly, and we'll just do KQ over r squared. So now let's find what is the electric field when we're in this outer shell. Now the problem says that the outer shell is a conducting shell, and so again, all the charge must be on the surface because they're pushing each other away. And the other thing is that the electric field within a conducting object must be 0. So that means that the charge enclosed must be equal to 0 if our sphere is within the shell. Because it's 0, this Q, this is negative Q, R is less than B, greater than B, but less than C. Electric field has to be 0. And in order to make that 0, the inner surface of the shell will have to be negative Q in order to make this charge enclosed net to be 0. If this is negative Q and the net is 0, the outside must be positive Q. So if R is greater than C, then the electric field will just be Q over this is they'll be the same. So then next it asks to sketch the electric field as a function of R. So if this is R, this is the electric field. It goes from, say this is A, and then we go to B, and then C. So it's 0 at this point. And then when it goes here, it's proportional to R squared, to the inverse of R squared. So there will be an immediate jump here, and it'll come down proportional to negative R squared, inverse of R squared. And then from B to C, it is 0. So I believe looks like this. Back to 0. And then as it gets bigger, it gets smaller. What is the charge on the inner surface? I'm going to have to double check this section. But the charge on the inner surface of the shell has to be negative Q. Charge on the outer surface has to be positive Q. Sketch the electric field lines outside of the shell. Really should just be radiating outwards.